Hi everyone, welcome to the Exam 3 review. Before we begin, I have a couple important reminders and suggestions for you. First, a calculator will be extremely useful on this test. Please go put your calculator in your backpack right now. Put it in your car or write a sticky note and put it on your front door. Write a note on your hand so you remember. It is not the responsibility of the TAs to bring extra calculators, and you will really want a calculator for this exam. My next suggestion is that you go take that amazing practice exam that Dr. Henry has provided for you. It is an incredibly good representation of these concepts and what will be on the exam. It will be most useful to you if you try to take that quiz without any notes. Have scratch paper ready so that you can sketch out your ideas and calculate test statistics, and then come back to this review so you can focus on the concepts that you missed. Ultimately, that will save you time and will be the best way to remember these concepts on the actual test. Finally, just remember your good test-taking strategies like looking over the whole exam and try not to get stuck on one frustrating question. Even when I was taking the exam, I found that by the end of the exam, I actually remembered something that applied to an earlier question that I had gotten really stuck on and had ended up wasting a little bit of time. So just be mindful that even if something doesn't come to you in the moment, you can move on, answer the questions that you can, and it may happen that you remember how to sketch it out or what little mistake you were missing as you go through the exam. Try to take a deep breath. I know that these kinds of materials are very difficult, and I'm super proud of the way that everyone has been engaging, so keep up the great work. Okay, for this exam review, I am going to take the Module 7 example data and I'm going to step through the steps provided in Module 11. If you want to have the Module 11 steps open on the side, that might be helpful to you, but I will try to include everything in the slides as we go. So anytime I see a question, before I even look at what the question is about, I always ask myself, what information am I given? And so in this case, we are going to be given some information like the averages, the estimate and standard error for the intercept and slope. And as a reminder, the Module 7 example is about the agreement with updated recommendations for sanitizing your phone based on either a control treatment or a control condition or the treatment condition where there was increased uncertainty in the messaging provided. The next question that I always ask myself is, what would this data look like? How can I sketch it out? Having a little sketch of your data will help you remember if your answers are looking like they make any sense, and it will help you keep straight things like the dependent and independent variable. So in this case, our little sketch might look something like this. We have the two conditions on the x-axis, and then the agreement with the updated recommendation on the y-axis. And we have a slope of 0.3, so that's a small positive slope. You can kind of sketch that out. The intercept is a 3.5-ish, and so I would just make myself a little drawing in the corner of my test so that I can orient myself to this data and have an idea of whether my future answers are making sense. The first step in Module 11 is to define the hypothesis. In this case, our null hypothesis is going to be that the acknowledgement of uncertainty, and that's the treatment condition, does not cause any change in adherence to updated public health guidance. So again, I might sketch this out in the same way with the same x and y axis, thinking that no change would be a pretty flat slope. Whereas my alternative hypothesis is acknowledgement of uncertainty increases adherence to updated public health guidance. And so I might draw another little graph with a pretty positive looking slope. But the really cool thing about these statistics that we're learning right now is that you cannot tell just from looking at that slope whether it's actually usefully different from zero. And only thanks to these statistics do we have a better idea of whether a real difference is being made by our treatment. Just a couple hundred years ago, we did not have these statistics, and people would just look at that slope and say, yes, it's positive, that's great, that we'll keep doing this treatment. And that is not a great way to continue determining things like public policy, medications, or anything. And so these statistics are a huge breakthrough that we should all be really thankful for, that we now have a better idea of whether the slope is actually different from zero. And so I also included this little snippet directly from Module 11. It is super important when you're reading research to be able to see and understand what these symbols mean. And so the null hypothesis is always indicated by this capital H with a subscript 0. And then that can be applied to different things, right? So in the first row there, you see that we're suggesting that the beta 0, or the true intercept for the population, is equal to 0. And in the next row, the alternative hypothesis would be that the beta 0 is not equal to 0. And so for the slope, which is mainly what we're going to focus on today, you would do the same thing. Your null, your H0, is going to be that beta 1, that's how we represent the slope, is that beta 1 is equal to 0. And then often the alternative hypothesis will just be that that slope is not equal to 0, that there was a change in any direction. But you may already have realized that in our alternative hypothesis, I selected a direction for that hypothesis. And so in this case, our alternative hypothesis would be that the true population slope is actually greater than 0. So this is going to become really important in our future steps. Next, we are going to determine the appropriate statistical test. And I just took this little snippet about why a t-test is the correct test straight from Module 11. I highly recommend you go back to Module 11 if you need any more details about why that is. So in this case, in order to do this t-test, there's a few things we need to remember. One very important equation to remember is the standard error equation. And as you can see, in the middle right of the slide here, the standard error, or SE, of y bar, which means average, the average of our sample, is equal to the standard deviation of our sample. So that's the SD is standard deviation, and the subscript y is of our sample. Anytime you see that little y, you're thinking of our sample, divided by the square root of the number of participants in our sample. So that's that little n, is number of participants in our sample. If you didn't have that equation really ready in your memory, I highly recommend you use some kind of fun learning technique to memorize it. This could be something like a flashcard. It could be something like writing it in a place that you'll often see it. It could be something like singing it to a song so that it's silly and you can have a better way to keep that in your memory over time. And so that when you're stressed out on the exam, it doesn't just evaporate. The other equation that is really important to remember is the t-test equation. And so I have 3 different versions displayed for you here, but I want you to remember that they're all getting at the same idea. What we're going to do is we're going to take our either y bar, that would be our average in the sample, the beta 0, that would be the intercept in our sample, or the beta 1, which would be the slope in our sample, and we're going to subtract the value that we determined for our null hypothesis. Now, in all of these cases, for us today, we're going to consider that to be 0. We said that for our slope, if the null hypothesis is true, the slope will be equal to 0. And so we're really focusing in on this very last, the bottom right version of the equation. But you can see that they're all really similar in getting at the same idea. We're taking into account the variability in our data to determine whether the relationship is really different from zero. So we've taken our slope, in this case, in the case of the bottom right, we're going to take our slope, we're going to subtract our null hypothesis value, which is 0, and then we're going to divide that by our standard error, which is how we take into account this variability in the data. And so as you can see in our sketch of the graph, all of our data points are not precisely in the exact area that our slope is going to point to. There's variability, there's differences in those answers. And if we didn't take that into account, we wouldn't have a true idea of whether our estimate is really different from zero. So you can also go back to Module 11 to get a better idea of why variability is so important. But for now, I'm kind of depicting it with this graph. And so we're taking everything in this graph, the slope, our null hypothesis, and the variability, and we're incorporating it into this t-statistic equation so that we can have an understanding of what's actually going on here. Step 3, define the rejection criteria. The first question I ask myself when I'm defining rejection criteria is this a one or two-tailed hypothesis? I really like to, and I highly recommend you, sketch out a normal curve for your null hypothesis to help orient you to this idea. Remember that our null hypothesis is that the slope will be 0, and so I've sketched out a normal curve with the slope, with the highest point at 0. Okay, and if you go back to our null and alternative hypothesis, you'll see that we had an alternative hypothesis suggesting that the slope would be greater than 0. And so that's going to be on this right-hand side. Now the number doesn't really matter at this point. Just sketch out that normal curve so that you know which of these tails is important to you and what that might look like so you can kind of check your answers as you go. So in this case, since we're looking for an increase, it'll be this right-hand tail. If we would have said just that there will be a difference from 0, that would be both tails. And if we said there would be a decrease, that would be just the left-hand tail. Now remember that just because we're only interested in the right-hand tail doesn't mean that we can look at this graph in a way that isn't symmetrical. That other tail is still going to be out over there. We just don't care about it. Okay, that'll become important in a second. If that's not clear to you now, I hope to make it a little more clear as we go through this slide. So we have a one-tailed hypothesis. Next, we need to know our degrees of freedom. You may remember that degrees of freedom for an intercept or slope is going to be the number of participants, or n, minus 1, minus the number of predictors. In this case, our only predictor is going to be that control and treatment condition. But if I would have maybe controlled for years of education, that would be an additional predictor that I would have to add to this equation to calculate my degrees of freedom. But in this case, we're just looking at one predictor, so it would be n minus 2. Our n was 442. If you go back to the first slide, you'll see where I got that from. So our degrees of freedom is going to be 440. If I was looking at this on an exam, I might write in the little corner, degrees of freedom equals 440, so that I would have that number to work with as I go. Next, we need to know our alpha. Now, remember that alpha is determined by researchers as the amount of risk they're willing to take for a type 1 error. And remember, a type 1 error or a false positive is going to be when we reject the null hypothesis when really the null hypothesis was true. And so a very common alpha is the 0.05. That is the alpha that we are going to work with. Now I have my degrees of freedom, I have my alpha, I'm ready to use this QT function, which you might remember provides that critical T number that we need in order to define our rejection criteria. So we might think, okay, our alpha is 0.05, 0.05 minus 1 is 0.95, we'll put that in. Our degrees of freedom is 440, but no, that's not right. In fact, this is a mistake that I made and that I had a really hard time figuring out where I went wrong. And so I have made this mistake intentionally on this slide to remind you of this very important concept. When your alpha is 0.05, that whole alpha is not going into your right-hand tail. The alpha is always still split between those two tails. We just don't care about the left-hand tail. And so you have to stop yourself. This is not the right way to use the QT function. What you need to do is split that 0.05 into 0.25 on either side of that normal curve. Now we subtract 0.25 from 1. That's how we get our 0.975. That actually represents this tail that we are interested in, and our degrees of freedom will still be the same. So be very careful. If you are getting confused on a question like this, double check your drawing. Just because I've only labeled the rejection region on the right-hand side here doesn't mean that the other tail isn't taken into account. You still have to have in your mind the idea that this alpha is going to be split on either side of this normal curve. And why is this super duper important? Because we're using this to define our rejection region. And if I define our rejection region based on that first QT output, I'm getting a different number than if I use the correct QT output. And that will change everything that we're looking at in the future. If we get this wrong, it's really hard to get future steps correct. Step 4, calculate the test statistic. This is when things get really exciting. We are going to put numbers into these equations we have been talking so much about, and we're then going to use this test statistic to determine whether we can reject our null hypothesis. So in order to do this, we are going to focus on the slope, which is that lower of the two general equations, but I wanted to include the equation for the intercept just to remind you that you can go about this in the same way to determine whether the intercept falls in your, if your intercept's t statistic falls in your rejection region. So for the slope, we'll start by looking at that estimate column in the condition.f treatment row, and we're going to use that 0.3001638. We're going to subtract the value that we said the slope would be if our null hypothesis was true, in this case 0. And we're going to divide by that standard error in the std.error column under the condition.f treatment row. That's the 0.1145675. When we calculate that, it is going to be approximately equal to 3. Step 5, determine if the calculated test statistic is in the null hypothesis rejection region. All we're going to do now is go back to that little sketch we had made previously where we told ourselves where our rejection region is. We're going to check out whether our t statistic falls in that region or not. And that's pretty much as easy as it is. If you've been doing the sketches along the way, it makes it a lot easier just to plop your test statistic right on top and not have to go back and consider where all those numbers are going to fall into place. So that's why I really recommend you start by drawing that normal curve of your null hypothesis. Now it's finally time to reject or not reject our null hypothesis. Since you clearly saw in the sketch on the previous slide that our t-statistic fell in our rejection region, you're already probably thinking that we will reject our null hypothesis. But there is another way to go about this as well. We could use the PT function to get our p-value. And so if you don't remember what the deal is with the PT function, this might be a great time to go back to that module and gather those details. But in this example, I will tell you, we would make our Q equal to our test statistic, which was about 3. Our degrees of freedom would be the same that we calculated before because we wrote that down and have it in the corner of our piece of paper, and so it's handy. We don't even have to think about that. And remember, since we're only looking at the right-hand tail, we can make the lower tail false. If we wanted to look at a two-tailed hypothesis, we would have to add the value for the other tail, which we would do by taking the negative of our t-statistic and then adding that, and then we would not have to include the lower tail equals false. There's a great example of this in the module. I highly recommend you make sure you go back and understand that. Now that we have rejected our null hypothesis, let's calculate some confidence intervals. Now, if you don't remember the difference between the percentile and standard error methods for calculating confidence intervals on Bootstrap data, I highly recommend you go back to the module and remind yourself how to calculate confidence intervals in percentile and standard error methods. Make sure that you not only understand the difference, but can recognize and apply each of those methods. If you have any questions about those, please reach out and let me know. In this case, we will calculate the confidence interval by taking our estimate for the slope, adding or subtracting the critical t-value, and multiplying by the standard error. So our slope was about 0.3. We're going to add and subtract our t-critical value that we used to define the rejection region. And we're going to multiply by our standard error, which was about 0.11. Please forgive my ugly rounding. I was just getting really tired. Don't make this mistake and round before the end of the equation in your own work. It is typically expected that you would use all decimal places until your final answer and then round that. So when you calculate this out, your lower bound will be about 0.08 and your upper bound will be about 0.516. And so you may remember that this means you could interpret this to mean that in the long run, if we were to repeatedly collect samples and calculate the 95% confidence interval, we would expect about 95% of those intervals to contain the true population slope. If that sentence didn't sound very familiar to you, I highly recommend you go back and look at Module 11 and make sure that you do understand the interpretation of confidence intervals. If you have any questions on that, again, please reach out to me. That concludes our Exam 3 review. I want to thank you for your time and energy in this class and let you know that I am available over break to answer emails. I will also be having additional office hours on the Monday after break, as well as my normal office hours on the Wednesday after break. Good luck in your studies and have a great rest of your day.